Welcome to video 3 of lecture 2 on evolvable hardware analog systems. So in the last video we saw one example from the NASA team on looking at designing a new chip. So what I want to do now in this final video of lecture 2 is give a couple more examples of work that's been done on analog evolution. So the first of these I've called intrinsic analog evolution, and you'll see, if you remember, intrinsic means on chip. So this is the team based in Japan, and they were looking at the problem of cellular phones and to do with filters in cellular phones. And they wondered whether they could produce an analog evolvable hardware chip to solve a particular problem that a company that was producing mobile phones was having. So they wanted to look at doing offline analog evolvable hardware, but it was actually on chip. So it was actually on the device. And what they were looking at is the intermediate frequency filter on these phones. So in fact, it was an analog bandpass filter, as we'll see the characteristics in a minute. The requirement was that it must have a small number of take up a small area and be fast, and there was a very large market for this, obviously, because it was going to end up in mobile phones and cellular phones. So there was a large market for such a thing. And the problem they were facing was the variations of the analog components on the phone that was being produced meant that what they wanted to do, what they needed to do, is after fabrication, so after the chips were actually made, they needed to do adjustments to these chips. And if they didn't do this, they found that the yield of the chips reduced significantly. So that was the problem they were faced with. And could they use evolvable hardware to solve this particular problem? So this is a picture of the filter. So here we've got the filter. In fact, it's made up of a number of op-amp stages, with obviously some passive components around those, and you could effectively adjust the bandwidth of these op-amps by the current that was being this current here going into these op-amps. If you remember back in the first video of these, we saw that we could actually change bandwidths of op-amps by changing the functionality. So what they produced, so this was the chip that was being built, and what they did was they augmented it with effectively a genome here, a chromosome, and each of these bits or series of bits affected the current that was going down from each of these op-amps, which then in turn affected their characteristics. And then also, additionally on chip, then that they've got a small CPU which is running a GA, which has got the series of chromosomes and is doing the usual evolutionary system to do that. So it's by changing the characteristics of these transconductance amplifiers through this bit stream, which was evolved using this GA. So that was the sequence of activities to do that. And the idea was, by doing that, what they were trying to do is get this intermediate bandpass filter back into characteristics after fabrication. So here we go. It is a slightly more detailed example. So now we're looking at these currents here, these bias currents for each of the transconductance amplifiers. So they could be varied only by a small amount, but that's all that was needed, by effectively switching in more or less of these constant current devices. So what it meant was that there was, if you like, a standard bias current, and then they could adjust it slightly with the configuration bit, either switching on or off different switches to feed in more current drains as the system was done. Okay, so basically it was a bias current controller. Okay, as it said here, that the GA sought to optimize the configuration bits to tune these devices, and then measure the gain and the frequency response of these devices through the evolutionary loop. So here's a picture of what they wanted. So this is the frequency range, so it's in the kilohertz range. Okay, and it's a bandpass filter. And if you focus in on the important part at the top here, then that's the characteristics you'd expect it to be receiving. And in fact, what they found was the most important thing was what was happening around these 3 dB points. So where the characteristics of the circuit were going around here. So it didn't matter so much here if it wasn't quite the same here, and maybe at the top here it might dip or something slightly at the top here. But the important point was that it goes through these if you like gates at the 3 dB points, and that actually then improved the response of the circuit. So what they did was they found that the bias currents would effectively control, or they could measure a number of characteristics of each of these filters as the bias currents were there. So one was the center frequency, so the W's of these filters at different frequencies, okay? Then the bandwidth, and also the filter gains at each one. So given an input and an output, and they could measure the response, and the bias currents were allowed to change these parameters effectively on these circuits. So this is what they found. This is a typical example. So this is what might come off the production line. So remember, these chips had already been made at this point. So you might get a characteristic like this because of the various components in the circuit. And what the GA was able to do was change the characteristics of this by changing those bias currents, so that the gain actually now met the spec. As I said, it didn't quite so matter what was going on here in the middle, or maybe even at the sides, but it had to get through these 3 dB point gates, if you like, to make it work properly. So that was really successful. And at that point, evolution stopped. So this wasn't something where evolution kept going. This is a one-off thing to actually get evolution to bring things in the spec, and then evolution was stopped. And what they found was that the yield rate went up to somewhere between 90 and 100% on these devices by doing that. So this is the whole device on the chip, the photo of the die here, and it says improves the yield rate significantly, and it was applied to a wide range of analog circuits, and not just, in fact, this foam one. So this group did a lot of work on designing chips for that. So this is a really nice example of how evolvable hardware can be used for a practical example, and produce some really nice results from that. Okay, so let's go on to a second example. And so this is slightly different, optimizing a static SRAM cell or cells. Okay, and this is actually a really important thing in this day and age. So memory cells form significant parts of many electronic designs, and standard processing systems have large amounts of SRAM and other types of memory these days. FPGAs have SRAM configured all around the device. Hence, to be able to actually optimize these can make a big difference to the operation of a system, maybe the speed of the system, or even the power. If we can optimize it for reducing power of these devices, then actually it's prevalent across many systems. So this is the device. In fact, this is some work we did at York. So this is a device cell that we were optimizing. So in fact, it's a 10T SRAM cell. So it's got 10 transistors. The original design was by ARM down here. And if you're interested, this is the paper down here, which actually talks in detail about how this design was made. So it's very much like a normal SRAM design. There are extra transistors in there to get the lower power and other characteristics that they were looking at. So it's a slightly more complex circuit than you might expect for a standard SRAM cell. So what would we want to optimize? What we want to measure? I mean, one of the things with evolutionary loops is that you need to measure something to see whether one circuit is better than the other. Well, figures of merit for SRAM cells, there's lots, and it depends somewhat on the application of what your particular figure of merit was. But for this particular application, we were looking at these 6 figures of merit. So static noise margin, write margin, the read current compared to I read, the leakage current, the ratio of the read current to the leakage, and the area, so how much area it's taking up. Okay. And in this particular evolutionary optimization problem, we actually were looking at all of those at the same time. So one of the nice things about evolutionary systems is that you can actually perform multi-objective optimization at the same time. And of course, one of the issues with looking at these figures of merit is what you'll find is if you improve one, you'll find 2 or 3 of the others get worse. So it's not just a simple reduce or increase, whatever the parameter is, to make things better. They're actually interdependent. So it makes it quite difficult to do by hand, if you like. And it's a perfect example of where evolution might come in to help you do a design. So this is some results that were applied to that circuit. So what you see here, so as we said, we've got all of these figures of merit, 6 figures of merit, but it's kind of difficult to illustrate all those on one graph. So this is just showing 2 of those. So this is area against I read, so the read current. And what you'll see on here is each one of these is the design. So each green dot is a design. What evolution has done, and this is a multi-objective evolutionary system, it's given you lots of options. So this option here minimizes, is close to minimizing the area, but it might have other, you'll see it's not got such a high read current. Whereas this one up here maximizes the read current, but it's got a bigger area. And this is where the conflicting parameters come in. So depending on where you want your design, what you're actually looking for your design to do, whether it's maybe a maximum read current or whether it's minimizing area, you could pick one of these designs. If we look in a little bit more detail, what you'll see is quite difficult to see really, but what evolution has done in this particular SRAM thing, the configuration is the same. So that's not changed across all of the designs. What's changed is actually the size of the transistors. So the width and length of the transistors, not all of them, but some of them. So for example, you'll see this transistor here is 310 by 60 for minimizing area. And for the one in the middle, the good trade-off one, it's 310 by 110. Okay, and if you want to maximize read current, it goes up to 585 by 165. So the length and the width of the transistors are changing all the time, or in many of the cases, to maximize for those things. So this was a really nice example of showing evolution in action to actually solve a common problem. And so what you can see here, so this is our 6 figures of merit, and this was the initial unoptimized design, and these are the parameters for each of these, because remember the graph only showed us 2, so this one shows all 6 in this table for the design that minimized area, the design that maximized read current, and the one that was a good trade-off. And this one at the end here was a design done in that paper that I referenced before. So you can see that it was kind of an interesting example of how evolution can come up with a new design for you, one that was better than the human design. So, and of course, a single cell in an SRAM is not so useful. So typically, these cells would then be put in a column. In this particular case, 64-bit cell. And then you've also got extra hardware, if you like, on either side. So you've got pre-charged circuits, and you've got drive circuits, and you've got sense amplifiers to see whether it's a 1 or a 0. So it then becomes a much more complex problem. So what we did was we did that, and then we apply the evolution again. So again to that more complex circuit. But again, it shows that, again, I've showed I read against area. And what we can see is, again, we can apply the evolution to that more complex circuit to try and optimize the individual cells, which then optimize the whole column within the circuit. So that was a nice example of showing that. And then, so this is at the design level. So the one I showed before in Japan was obviously after fabrication. So this would be done before fabrication to optimize the designs before you went to fabricate an SRAM cell. So what applications in industry might evolvable hardware be useful for? So things where we've got processes that are adapting. So maybe going back to the NASA example where we need adaptation for the temperature. That was a nice example. Where we've got complex optimization problems. So the SRAM cell is an example of that. Where things are going wrong. Analog circuits, I think they're more interesting for evolution than digital ones. The digital ones are maybe more straightforward in design processes, where analog is trickier. Unknown environments, so where we actually want things to change because we don't know what it's going to face. and also robotics. And we'll see an example in robotics in the next lecture. So promising application domains. So analog devices, I've mentioned those, and we've talked a lot about those in this lecture. Optical systems, so we've not talked about optical systems, and we won't in just these 3 lectures. But over here is an example where there was a complex setup of a laser system with mirrors to control the system and the light sources. And these systems have multiple points where the small adjustments need to be made so that everything works very well. And there has been some work of actually putting each of the adjustment systems on a small stepper motor and getting evolution to adjust the stepper motors to actually optimize the position of all the mirrors and the light sources. Autonomous robotics. So there's been quite a lot of work where, given a robot, the controller of the robot, if you like, the brain of the robot evolves for a particular application. Mechanical designs. So in fact, some of the very early work on evolution was actually done on mechanical designs. Some interesting work that's recently been done is actually trying to evolve physical structures. So in this particular case, this is an example of an evolutionary system going around this loop, around the outside up to there, where it's evolving a table. So, okay, we know how to build a table, but it may be interesting in the future for other structures. Robot design. So we'll talk a little bit of this in the next lecture. And here's an example of a robot which both the body plan and ultimately the controllers are all designed by evolution rather than by humans. And medical engineering. So this is an example of a prosthetic hand where, because of the signals that from everybody's brain is different, what this system did, and this is in fact from the group from Japan again, that we saw the first application in this video, they had an evolvable hardware controller chip which evolved itself to individuals. So the hands were the same, but the signals coming into them were different for different people, and this system effectively learnt the signals for an individual to optimize the movement for the hand. So it was a really nice application for that. So finally, for lecture 2, here's a few more references. So the first one is related to the work from the guys in Japan on the mobile phone, and the next 2 are more to do with the SRAM cell and using evolution for doing that. So as a final set of questions before we get to lecture 3, okay, so we've seen that we can actually do evolution on hardware. Okay, but how do we think they might help when it comes to variability in semiconductor fabrication and therefore device reliability? And how might we use it for designing robots? Okay, not just the controllers, but body parts as well. Okay, so that will be the subject of lecture 3 in this series. Thanks very much.